This is Color from 19. Today is day 6 in my challenge day. And today I'm going to learn derivatives of activation functions and gradient descent for neural networks and backpropagation intuitions. Mm, If we, if I have enough time, I will just finish until the random initialization. Okay, let's start.
Implement backpropagation for your neural network, you need to really compute the slope or the derivative of the activation functions. So let's take a look at our choices of activation functions and how you can compute the slope of these functions. Here's the familiar sigmoid activation function. And so for any given value of z, maybe this value of z, this function will have some slope or some derivative corresponding to, if you draw a little line there, the height over width of this little triangle here. So if g of z is the sigmoid function, then the slope of the function is e dz g of z. So we know from calculus that this is the slope of g of x at z. And if you are familiar with calculus and know how to take derivatives, if you take the derivative of the sigmoid function, it is possible to show that it is equal to this formula. And again, I'm not going to do the calculus steps, but if you're familiar with calculus, feel free to pause the video and try to prove this yourself. And so this is equal to just g of z times 1 minus d of z. So let's just sanity check that this expression makes sense. First, if c is very large, let's say c is equal to 10, then g of z will be close to 1. And so the formula we have on the left tells us that d dz g of z must be close to g of z, which is equal to 1 times 1 minus 1, which is therefore very close to 0. And this is indeed correct because when z is very large, the slope is close to 0. Conversely, if z is equal to minus 10, so say it's way out there, then g of z is close to 0. So the formula on the left tells us d dz g of z will be close to g of z, which is 0, times 1 minus 0. And so this is also very close to 0, which is correct. Finally, if z is equal to 0, then g of z is equal to 1 half. That's a sigmoid function right here. And so the derivative is equal to 1 half times 1 minus 1 half, which is equal to 1/4. And that actually turns out to be the correct value of the derivative or the slope of this function when z is equal to 0. Finally, just to introduce one more piece of notation, sometimes instead of writing this thing, the shorthand for the derivative is g prime of z. So g prime of z in calculus, the little dash on top is called prime. So g prime of z is a shorthand in calculus for the derivative of the function of g with respect to the input variable z. And then in a neural network, we have a equals g of z, right, equals this. Then this formula also simplifies to a times 1 minus a. So sometimes in implementation, you might see something like g prime of z equals a times 1 minus a, and that just refers to, the observation that g prime, which just means derivative. The advantage of this formula is that if you've already computed the value for a, then by using this expression, you can very quickly compute the value for the slope for e prime. All right, so that was the sigmoid activation function. Let's now look at the tanh activation function, similar to what we had pre-value for the slope for g prime. All right, so that was the sigmoid activation function. Let's now look at the tanh activation function. Similar to what we had previously, the definition of d dz g of z is the slope of g of z at a particular point of z. And if you look at the formula for the hyperbolic tangent function, and if you know calculus, you can take derivatives and show that this simplifies to this formula. And using the um, shorthand we had previously, we call this d prime of c again. So if you want, you can sanity check that this formula makes sense. So for example, if c is equal to 10, tan h of c will be very close to 1. This goes from plus 1 to minus 1. And then g prime of z, according to this formula, would be about 1 minus 1 squared. So it turns very close to 0. So that was if z is very large, it's close to 0. Conversely, if z is very small, say z is equal to minus 10, then tan h of z will be close to minus 1. And so g prime of z will be close to 1 minus negative 1 squared. So it's close to 1 minus 1, which is also close to 0. And if finally is equal to 0, then tan h of z is equal to 0. And then the slope is actually equal to 1, which is actually the slope when z is equal to 0. So just to summarize, if a is equal to g of z, so if a is equal to this tan h of z, then the derivative g prime of z is equal to 1 minus a squared. So once again, if you've already computed the value of a, you can use this formula to very quickly compute the derivative as well. Finally, here's how you compute the derivatives for the ReLU and leaky ReLU activation functions. For the ReLU, g of z is equal to x of 0, comma 0. So the derivative is equal to, turns out to be 0 if z is less than 0 and 1 if z is greater than 0. actually undefined, technically undefined if z is equal to exactly 0. But if you're implementing this in software, it might not be 100% mathematically correct. It'll work just fine um, if z is exactly root of 0, if you set the derivative to be equal to 1. Or if you set it to be 0, it kind of doesn't matter. If you're on exponent optimization, technically g prime then becomes what's called a subgradient of the activation function g of z, which is why gradient descent still works. But you can think of it as that the chance of z being, 0 point exactly 0.00000 is so small that it almost doesn't matter what you set the derivative to be equal to when z is equal to 0. So in practice, this is what people implement for the derivative of z. And finally, if you are training a neural network with the leaky relative activation function, then g of z is going to be max of, say, 0.01z comma z. Um, and so g prime of z is equal to 0.01 if z is less than 0 and 1 if z is greater than 0. And once again, the gradient is technically not defined when z is exactly equal to 0. But if you implement a piece of code that sets the derivative or that sets g prime to either as 0.01 or to 1. Either way, it doesn't really matter. When z is exactly 0, your code will work just. So onto these formulas, you should be able to compute the slopes or the derivatives of your activation functions. Now that you have this building block, you're ready to see how to implement gradient descent for your neural network. Let's go on to the next video to see that. Alright, I think this will be an exciting video. In this video, you see how to implement gradient descent for your neural network with one hidden layer. In this video, I'm going to just give you the equations you need to implement to get back propagation or to get gradient descent working. And then in the video after this one, I'll give some more intuition about why these particular equations are the accurate equations, the correct equations for computing the gradients you need. The correct equations for computing the gradients you need for your neural network. So your neural network with a single hidden layer for now will have parameters W1, E1, W2, and B2. And so as a reminder, if you have an X, or alternatively N0 input features and N1 hidden units and N2 output units, in our example, so far I've only had N2 equals 1, then the matrix W1 will be N1 by N0. B1 will be an N1 dimensional vector, so you can write that as an N1 by 1 dimensional matrix, really a column vector. The dimensions of W2 will be N2 by N1, and the dimension of B2 will be N2 by 1. Right, where again, so far we've only seen examples where N2 is equal to 1, where you have just one single hidden unit. So you also have a cost function for your neural network. And for now, I'm just going to assume that you're doing binary classification. So in that case, the cost of your parameters as follows is going to be 1 over m of the average of that loss function. And so L here is the loss when your neural network predicts y hat, right? This is really A2 when the ground truth label is equal to yn. If you're doing binary classification, the loss function can be exactly what you use for logistic regression earlier. So to train the parameters of your algorithm, you need to perform gradient descent. When training a neural network, it's important to initialize the parameters randomly rather than to all zeros. We'll see later why that's the case, but after initializing the parameter to something, right, each loop of gradient descent would compute the predictions. So you basically compute y hat I for I equals 1 through m, say, and then you need to compute the derivatives. So you need to compute dw1, and that's basically the derivative of the cost function with respect to the parameter w1. You need to compute another variable called db1, which is the derivative or the slope of the cost function with respect to the variable b1, and so on. Similarly for the other parameters w2 and b2. And then finally, the gradient descent update would be to update w1 as w1 minus alpha, the learning rate, times d w1. b1 gets updated as b1 minus the learning rate times d b1. And similarly for important to initialize the parameters randomly routed into all zeros. We'll see later why that's the case, but after initializing the parameter to something, right, each loop of gradient descent would compute the predictions. So you basically compute y hat I for I equals 1 through m, say, and then you need to compute the derivative. So you need to compute dw1, and that's you see the derivative of the cost function with respect to the parameter w1. You need to compute another variable, which I'm going to call dp1, which is the derivative or the slope of the cost function with respect to the variable p1, and so on. Similarly for the other parameters w2 and p2. And then finally, the gradient descent update would be to update w1 as w1 minus alpha, the learning rate, times d w1. p1 gets updated as p1 minus the learning rate times d p1. And similarly for w2 and p2. And sometimes I use colon equals, sometimes equals, as either notation works fine. And so this would be one iteration of gradient descent, and then you repeat this some number of times until your parameter is locally converging. So in previous videos, we talked about how to compute the predictions, how to compute the outputs, and we saw how to do that in a vectorized way as well. So the key is to know how to compute these partial derivative terms, the dw1, dp1, as well as the derivatives dw2 and dp2. So what I'd like to do is just give you the equations you need in order to compute these derivatives. And I'll defer to the next video, which is an optional video, to go greater into depth about how we came up with those formulas. So let me just summarize again the equations for forward propagation. So you have C1 equals W1x plus B1, and then A1 equals the activation function in that layer applied element-wise to C1. And then Z2 equals W2 A1 plus B2. And then finally, this is all vectorized across your training set. Right? A2 is equal to G2 of Z2. But again, for now, if we assume you're doing binary classification, then this activation function really should be the sigmoid function. So just throw that in here. So that's the forward propagation or the vector right forward computation for your network. Next, let's compute the derivatives. So this is the back propagation step. We're going to compute dz2 equals a2 minus the ground truth y. And just as a reminder, all this is vectorized across examples. So the matrix Y is this 1 by M matrix that is also, then it turns out dw2 is equal to this. And in fact, these first three equations are very similar to gradient descent for logistic regression. This one, comma, um, keep this true. And just a little detail, this np.sum is a Python NumPy command for summing across one dimension of a matrix, in this case, summing horizontally. And what keepdims does is it prevents Python from outputting one of those funny rank 1 arrays, right, where the dimensions was, n comma. So by having keepdims equals true, this ensures that Python outputs for dp2 a vector that is n by 1. In fact, technically this will be, I guess, n2 by 1. In this case, it's just a 1 by 1 number, so maybe it doesn't matter, um, but later on we'll see when it really matters. So far what we've done is very similar to logistic regression, but now as you continue to run back propagation, you would compute this. dc2 times 1 prime of z1. So this quantity g1 prime is the derivative of what was the activation function you use for the hidden layer. And for the output layer, I assume that you're doing binary classification with the sigmoid function, so that's already baked into that formula for dc2. And this times is an element-wise product. So this here is going to be an n1 by m matrix, and this here, this element-wise derivative thing is also going to be an n1 by m matrix, and so this times there is an element-wise product of two matrices. Then finally, dw1 is equal to that, and db1 is equal to this, and p dot sum dc1 x is equals 1, keep dims equals true. So whereas previously the keep dims maybe matter less if n2 is equal to 1, so this is just a 1 by 1 thing, it's just a real number. Here, db1 will be a n1 by 1 vector, and so you want Python, you want np.sum to output something of this dimension rather than a funny rank 1 array of that dimension, which could end up messing up some of your data calculations. The other way would be to not have to keep the parameters, but to explicitly call, reshape, to reshape the output. So, this dimension that you would like db to have. So that was forward propagation in, I guess, 4 equations, and back propagation in, I guess, 6 equations. I know I just wrote down these equations, but in the next optional video, let's go over some intuitions for how the 6 equations for the back propagation algorithm were derived. Please feel free to watch that or not, but either way, if you implement these algorithms, you will have a correct implementation of forward prop and back prop, and you'll be able to compute the derivatives you need in order to apply gradient descent to learn the parameters of your neural network. It is possible to implement this algorithm and get it to work without deeply understanding the calculus. A lot of successful deep learning practitioners do so. But if you want, you can also watch the next video just to get a bit more intuition about the derivation of these equations. In the last video, you saw the equations for backpropagation. In this video, let's go over some intuition using the computation graph for how those equations were derived. This video is completely optional, so feel free to watch it or not. You should be able to do the homework either way. So recall that when we talked about logistic regression, we had this forward pass where we would compute z, then a, and then a loss. And then to take derivatives, we had this backward pass where we could first compute dA, and then go on to compute dz, and then go on to compute dw and db. So the definition for the loss was L of a comma y equals negative y log a minus 1 minus y times log 1 minus a. So if you're familiar with calculus and you take the derivative of this with respect to a, that would give you the formula for dA. So dA is equal to that. And if you actually figure out the calculus, you can show that this is y over a, negative y over a, plus 1 minus y over 1 minus a. Just kind of derive that from calculus by taking derivatives of this. It turns out when you take another step backwards to compute dz, we then worked out that dz is equal to a minus y. I did explain why previously, but it turns out that from the chain rule of calculus, dz is equal to dA times d prime of z, where here g of z equals sigmoid of z is our activation function for this output unit in logistic regression, right? So just remember, this is still logistic regression. We have x1, x2, x3, and then just one sigmoid unit, and then that gives us a, gives us y hat. So here, the activation function was a sigmoid function. And as an aside, only for those of you familiar with the chain rule of calculus, the reason for this is because a is equal to sigmoid of z, and so partial of L with respect to z is equal to partial of L with respect to a times dA dz. But since a is equal to sigmoid of z, this is equal to d dz e of z, right? Well, this, which is equal to g prime of z. So that's why this expression, which is dz in our code, is equal to this expression, which is dA in our code, times g prime of z. And so this is just that. So that last derivation would make sense only if you're familiar with calculus and specifically the chain rule from calculus. But if not, don't worry about it. I'll try to explain the intuition wherever it's needed. And then finally, having computed dz for logistic regression, we'll compute dw, which it turns out was dz times x, and dp, which is just dz. We have a single training example. So that was logistic regression. So what we're going to do when computing backpropagation for a neural network is a calculation a lot like this, but only we'll do it twice, because now we have not x going to an output unit, but x going to a hidden layer, and then going to an output unit. And so instead of this computation being sort of one step as we have here, we'll have, two steps here, right? In this kind of a neural network with two layers. So in this two-layer neural network, that is with an input layer, a hidden layer, and an output layer, remember the steps of a computation. First, compute Z1 using this equation, and then compute A1, and then you compute Z2, and notice Z2 also depends on the parameters W2 and B2, and then based on Z2, compute A2, and then finally, that gives you the loss. So what backpropagation does is it will go backward to compute dA2 and then dZ2, and then go back to compute dW2 and dB2, go back to compute dA1, dZ1, and so on. Okay. But we don't need to take derivatives with respect to the input x, since the input x for supervised learning is fixed, so we're not trying to optimize x, so we won't bother to take derivatives, at least for supervised learning with respect to x. And so I'm going to skip explicitly computing dA2. If you want, you can actually compute dA2 and then use that to compute dZ2, but in practice, you can collapse both of these steps into one step, so you end up that dZ2 is equal to A2 minus Y, same as before. And you have also, we're going to write dW2 and dB2 down here below. You have that dW2 is equal to dZ2 times A1 transpose, and db2 equals dc2. So this step is quite similar to for logistic regression. dw was equal to dz times x, except that now a1 plays the role of x, and there's an extra transpose there because the relationship between the capital matrix W and our individual parameters W was there's a transpose there, right? Because W is equal to a row vector in the case of logistic regression with a single output. dw2 is like that, whereas W here was a column vector, so that's why there's an extra transpose for a1, whereas we didn't for x here for logistic regression. So this completes half of back propagation. And then again, you can compute dA1 if you wish, although in practice, the computation for dA1 and dZ1 are usually collapsed into one step. And so what you can actually implement is that dZ1 is equal to W2 transpose times dZ2, and then times an element-wise product of G1 prime of C1. And just to do a check on the dimensions, right? If you have neural network that looks like this, right? Outputs y. So if you have n0 and x equals n0 input features, n1 hidden units, and n2 so far, and n2, in our case, just one output unit, then the matrix W2 is n2 by n1 dimensional Z2, and therefore dZ2 are going to be n2 by one dimensional. It's really going to be a one by one when we're doing binary classification. And Z1, and therefore also dZ1, are going to be n1 by one dimensional. Right? Note that for any variable foo and dfoo always have the same dimension. So that's why w and dw, always have the same dimension. And similarly for b and dp and c and dz and so on. So to make sure that the dimensions of this all match up, we have that dz1 is equal to w2 transpose times dz2, and then this is an element-wise product times G1 prime of C1. So matching the dimensions from above, this is going to be N1 by 1 is equal to W2 transpose for transpose of this. So this is going to Z2 is going to be N2 by one dimensional. And this is the same dimension as C1. So this is also N1 by one dimensional element-wise product. So the dimensions do make sense, right? A one-dimensional vector can be obtained by n1 by n2 dimensional matrix times n2 by n1, because the product of these two things gives you an n1 by one-dimensional matrix. And so this becomes the element-wise product of two and one by one dimensional vectors. And so the dimensions do match up. One tip when implementing backprop, if you just make sure that the dimensions of your matrices match up, so if you think through what are the dimensions of your various matrices, including W1, W2, Z1, Z2, A1, A2, and so on, and just make sure that the dimensions of these matrix operations match up, sometimes that will already eliminate quite a lot of bugs in background. All right, so this gives us DZ1, and then finally, just to wrap up, DW1 and DB1, I really should write them here, I guess, but since I'm running out of space, I'll write them on the right of the slide. DW1 and DB1 are given by the following formulas. This is going to be equal to dz1 times x transpose, and this is going to be equal to dz. And you may notice a similarity between these equations and these equations, which is really no coincidence because x plays the role of A0, so X transpose is A0 transpose. So those equations are actually very similar. All right, so that gives a sense for how backpropagation is derived. And we have six key equations here for um, dz2, dw2, db2, dz1, dw1, and db1. So let me just take these six equations and copy them over to the next slide. Here they are. And so far, we've derived backpropagation for if you're training on a single training example at a time. But it should come as no surprise that rather than working on a single example at a time, we would like to vectorize across different training examples. So we remember that for propagation, when we're operating on one example at a time, we had equations like this, as well as say A1 equals G1 of Z1. And in order to vectorize, we took, say, the Z's and stacked them up in columns like this, M, and called this capital Z. And then we found that, by stacking things up in columns and defining the capital uppercase version of these, we then just had C1 equals W1x plus B, and A1 equals G1 of Z1, right? And we define the notation very carefully in this course to make sure that stacking examples into different columns of a matrix makes all this work out. So it turns out that if you go through the math carefully, the same trick also works for backpropagating. So the vectorized equations are as follows. First, if you take these DZs for different training examples and stack them as the different columns of the matrix, and same for this, and same for this, then this is the vectorized implementation. And then here's the definition or here's how you can compute dw2. There is this extra 1 over m because the cost function k is this 1 over m of sum from I equals 1 through m of the losses. And so when computing derivatives, we have that extra 1 over m term, just as we did when we were computing the weight updates for logistic regression. And then that's the update you get for db2. Again, sum of the dz's and with a 1 over m. And then dz1 is computed as follows. Once again, this is an element-wise product. Only whereas previously, we saw on the previous slide that this was an n1 by 1 dimensional vector. Now this is a n1 by m dimensional matrix. And both of these are also n1 by m dimensional. And so that's why that asterisk is our element-wise product. Right. And then finally, the remaining two updates perhaps shouldn't look too surprising. So I hope that gives you some intuition for how the backpropagation algorithm is derived. In all of machine learning, I think the derivation of the backpropagation algorithm is actually one of the most complicated pieces of math I've seen. And it requires knowing both linear algebra as well as the derivative matrices to really derive it from scratch, from first principles. If you're an expert in matrix calculus, um, using this process, you might be able to derive the algorithm yourself. And I think that there are actually plenty of deep learning practitioners that have seen the derivation at about the level you've seen in this video and are already able to have all the right intuitions and be able to implement this algorithm very effectively. So if you are an expert in calculus, do see if you can derive the whole thing from scratch. It is one of the very hardest pieces of math, very hardest derivations that I've seen in all of machine learning. Either way, if you implement this, this will work, and I think you have enough intuitions to tune it and get it to work. So with that, um, there's just one last detail I want to share with you before you implement your neural network, which is how to initialize the weights of your neural network. And it turns out that initializing your parameters not to zero, but randomly, turns out to be very important for training your neural network. In the next video, you'll see why. When you train your neural network, it's important to initialize the weights randomly. For logistic regression, it was okay to initialize the weights to zero, but for a neural network, if you initialize the weights to parameters to all zero and then apply gradient descent, it won't work. Let's see why. So you have here two input features. So n0 is equal to 2, and two hidden units. So n1 is equal to 2. And so the matrix associated with hidden layer W1 is going to be 2 by 2. Let's say that you initialize it to all zeros, so 0, 0, 0, 0, 2 by 2 matrix. And let's say B1 is also equal to 0, 0. Turns out initializing the bias terms B to 0 is actually okay, but initializing W to all zeros is a problem. So the problem with this form function is that for any example you give it, you will have that A11 and A12 will be equal, right? So this activation and this activation will be the same because both of these hidden units are computing exactly the same function. And then when you compute back propagation, it turns out that dz11 and dz12 will also be the same, kind of by symmetry, right? Both of these hidden units will initialize the same way. Technically, for what I'm saying, I'm assuming that the outgoing weights are also identical. So that W2 is equal to 0, 0. But if you initialize the neural network this way, then this hidden unit and this hidden unit are completely identical. Sometimes you say they're completely symmetric, which means that they're computing exactly the same function. And by kind of a proof by induction, it turns out that after every single iteration of training, your two hidden units are still computing exactly the same function. So it's possible to show that dw will be a matrix that looks like this, where every row takes on the same value. So when you perform a weight update, when you perform a weight update, W1 gets updated as W1 minus alpha times dw, you find that W1 after every iteration will have the first row equal to the second row. So it's possible to construct a group by induction that if you initialize all the weights, all the values of W to zero, then because both hidden units start off computing the same function and both hidden units have the same influence on the output unit, zero, then because both hidden units start off computing the function and both hidden units have the same influence on the output unit, then after one iteration, that same statement is still true. The two hidden units are still symmetric, and therefore, by induction, after two iterations, three iterations, and so on, no matter how long you train the neural network, both hidden retain exactly the same function. And so, in this case, there's really no point to having more than one hidden unit because they're all computing the same thing. And of course, for larger neural networks, let's say of three features and maybe a very large number of hidden units, a similar argument works to show that with a neural network like this, because I won't draw on all the edges, if you initialize the weights to zero, then all of your hidden units are symmetric, and no matter how long you run gradient descent, they'll all continue to compute exactly the same function. So that's not helpful because you want the different hidden units to compute different functions. The solution to this is to initialize your parameters randomly. So here's what you do. You can set W1 equals np.random.randn. This generates a Gaussian random variable 2, 2. And then usually you multiply this by a very small number, such as 0.01. So you initialize it to very small random values. And then B, um, it turns out that B does not have this symmetry problem. It's called the symmetry breaking problem. So it's okay to initialize B to just zeros because so long as W is initialized randomly, you start off with different hidden units computing different things, and so you no longer have this symmetry breaking problem. And then similarly for W2, you can initialize that randomly, and B2, you can initialize that to 0. So you might be wondering, where did this constant come from? And why is it 0.01? Why not put the number 100 or 1000? Turns out that we usually prefer to initialize the weights to very, very small random values. Because if you're using a, say, tanh or sigmoid activation function, or if you have a sigmoid even just at the output layer, if the weights are too large, then when you compute the activation values, remember that C1 is equal to W1x plus B, and then A1 is the activation function applied to C1. So if W is very big, Z will be very big, or at least some values of Z would be either very large or very small. And so in that case, you're more likely to end up at these flat parts of the tanh function or the sigmoid function, where the slope or the gradient is very small, meaning that gradient descent will be very slow, and so learning will be very slow. So just to recap, if W is too large, you're more likely to end up even at the very start of training with very large values of Z, which causes your tanh or your sigmoid activation function to be saturated. don't have any sigmoid or tanh activation functions throughout your neural network, this is less of an issue, but if you're doing binary classification and your output unit is a sigmoid function, then you just don't want the initial parameters to be too large. So that's why multiplying by 0.01 would be something reasonable to try, or any other small number. And same for W2, right? This can be a random block random. I guess this would be 1 by 2 in this example, times 0.01. So we see S there. So finally, it turns out that sometimes there can be better constants than 0.01. When you're training a neural network with just one hidden layer, this is a relatively shallow neural network without too many hidden layers, setting it to 0.01 would probably work okay. But when you're training a very, very deep neural network, then you might want to pick a different constant than 0.01. And in next week's material, we'll talk a little bit about how and when you might want to choose a different constant than 0.01. But either way, it will usually end up being a relatively small number. So that's it for this week's videos. You now know how to set up a neural network with a hidden layer, initialize the parameters, make predictions using forward prop, as well as compute derivatives and implement gradient descent using back prop. So with that, you should be able to do the quizzes as well as this week's programming exercises. Best of luck with that. I hope you have fun with the programming exercise and I look forward to seeing you in the week 4 materials.
So I just finished today's learning before I stop recording or just do a small recap. So today I learned how to implement like propagation in neural networks. First, we need a derivatives of activation function based on the process of forward propagation. So, oh no, just for activation functions. So here I aligned that the case of sigmoid and tonnage and ReLU and leaky ReLU, and these four ORHs of activation function that we derive it. Next, then we need to just uh, follow the same process what we did in logistic regression for gradient descent is also same. But in your network, because we have hidden layer, in logistic regression, we just calculate just one W and B from the activation function, which is a sigmoid. But in this case, we need to backpropagate more from the meter of activation function to previous G and also alpha. So we have these parameters, and the dimension of each parameters is based on the previous layer and next layer. And the gradient descent algorithm follows the compute predictions y hat I. Um, we can get each of derivatives by following these equations, and we can update each of parameters using a gradient descent. Actually, the backpropagate for DG1 and DW1 was quite difficult to understand from now on, just for now. So I just followed the what the professor wrote in his screen. So until DB2 is it's just same with logistic regression, but from DG1 we do element-wise product because the two matrices have same dimension. And for DW1 and DB1 is same with how to get the DW2 and DB2. And finally, I learned why the random initialization is important in your network, because initializing W with all zeros can occur some problem where the computation, wire compute, yes, wire computation. But it is okay to initialize the B with all zeros, which is bias. Um, so when we initialize W with all zeros, it means that the all hidden units in certain hidden layer become completely identical, which is called orthosymmetric, and also of hidden units to compute function with the same value, same function, and they also have same influences to output units. So by induction approach, because these first iteration it's turned out that it is true that compute same function and have same influences on output unit. It will be keeping on every iterations later on. So by the way, it is okay to we need to take on some another approach to initialize our parameters, especially with weights. The solution is to use randomization. We can just take this buffer tool to randomize our parameters with this NumPy library. And this multiplier means that because when we use a sigmoid function and tonnage function for activation, uh, as we already see, as we already seen, when the z is so huge and or small, becomes the gradients change so slightly where the g goes up or goes down. So it can be makes our neural network to learn so slow. So to avoid that, we can just uh, do some mul- multiply some small number to avoid this situation. Okay, this is end of this today's recording. Thanks for your watching.